He is going to talk about scattering and a Plancherel formula for real spherical varieties.
Yes, I thank very much the organizer to invite me to this conference. As I devoted most of my life to the Plancherel formula, like Harishchandra did. Okay, so I lectured already several times on this subject. Each time it generalizes and it becomes more correct. I hope these two things are stabilized. Okay. So this was the only love you will have during the hour, I think. Okay, so G will be a reductive group defined over R. P is a minimal parabolic of the real points. And X is a real spherical G variety with an invariant measure. So this means that X has an open P orbit. Spherical means that there is an open P orbit. And I assume for simplicity that P has a unique open P orbit. And the stabilizer, if X is the stabilizer of this P orbit, X is obviously isomorphic to G over H. So I come to the abstract Plancherel formula. So L2 is disintegrate in multiple of irreducible representation. Mu is a Borel measure on the unitary dual. The pi h pi are continuous irreducible unitary representation of G. And M pi, I insist on this notation that M pi is a multiplicity. So this will come back again. I will not say it each time, but M pi is a multiplicity. So M pi is a multiplicity. It's a finite dimensional space endowed with a scalar product and contained in the space of H-fixed distribution vectors which are tempered in a suitable sense. The goal is to explicit this formula up to the twisted discrete spectrum of the boundary degeneration of X. So I will come back to the definition of this object later. Twisted discrete series and boundary degeneration. The strategy is due to Sakaelis and Venkatesh in the p-adic case. This is to introduce Bernstein maps. I will come back to this. Is a work with Knopp, Kreutz, and Schrischkuhl over the real. And then with the help of an analog of their discrete series conjecture. You cannot read, but they made a discrete series conjecture, and I make also a discrete series conjecture that I will explicit. With X and P as above comes a non-unique maximal split torus, but I will fix one, A in P. And AMT is, by definition, A divided by A intersection H. And S is a finite set of simple spherical roots. I don't want to define them, but there are some rational characters of AMT. For I in S, Xi is equal to the boundary generation is G mod Hi, a boundary degeneration for hi some subgroup. I will explain later what is xi precisely. Let AI0, the neutral component of the Lie group AI, which is the intersection of the root in I, and it acts on xi by right translation commuting to the action to the left action of G. So this is this fact is very important. Z of G is the center of the complex enveloping algebra of G, and whereas the theory of the constant term, so here, what is it? It is a map between the Z of G finite tempered function on X and Xi. So this is analogous of the constant term of Harishchandra, but Harishchandra was doing something different. He was taking function on G and going to function on the Levy. Here we are going to function on G, on X and Xi. And now it's coming an important notation. So this notation, the constant term allows to define a map from H fixed tempered distribution vector to Hi fixed tempered distribution vector, eta to eta I. So this is this notation Gi pi. You have to have in mind that it is a map from distribution vector to distribution vector, and its adjoint will be also a map in the opposite side. Note that A0i acts on the left, on the space, on the right. One has something which is one is looking to the Plancherel formula for X, starting from the Plancherel formula for Xi. But here we have something opposite. One have the Plancherel formula. What is important in this formula is that the measure, the measure mu is the same for X and for Xi. It is very important. And Mi pi is also determined by M pi. It's a multiplicity. Okay. The scalar product on Mi pi is obtained by some process of limit from the one on M pi. Okay. But what is important is a measure. One has also the Mass-Selberg relations. Maybe I could. This is rather technical. So we have the weight space for Mi pi corresponding to chi. Then the map, the adjoint of Gi pi, which send Mi pi in M pi, is isometric. This is the version of Mass-Selberg relation. You have AI, the Lie algebra of AI, and you have L2 of X. You take lambda, unitary linear form on AI, and you have L2 of Xi lambda. This is a unitarily induced representation to G of the character Hi0 on Hi. and whose differential on AI0 is lambda. So you have a... No, merde. We have a character of HI0, which is trivial on HI, with differential on AI0 is lambda. So HI0 is a nice group. And then, what is the discrete spectrum when I have L2 of X TD? I say TD because of my friend and colleague Bernard Krauss. He said twisted discrete series because this is slightly different from relative discrete series. It's more complicated. So this is the discrete spectrum of L2 of X lambda, and twisted discrete series is the irreducible subrepresentation of L2 of X lambda. Okay. And one can define L2 of X E TD as the Hilbert integral of this representation. This is not so trivial because you have to prove some measurability condition to have the Hilbert, to have the to define the Hilbert integral. So I will come back to this below. Now I come to the analog of the discrete series conjecture of Sakaridis and Venkatesh. From Krauss, Kuit, Obdam, and Shishkrul, the real part of the Harish-Chandra parameters of infinitesimal characters of twisted discrete series are contained in a lattice. Okay. So the conjecture is the following. For I included in S and almost lambda in I star and all TD, there exists a Harish-Chandra parameter of the infinitesimal character of this TD, which is, with imaginary part is lambda. You have the real part, and the conjecture specifies the imaginary part of the infinitesimal character. So there are some, the conjecture is true in many cases for E equal S, because and S equal 0, because the infinitesimal character of discrete series is real. Or this is true also for factorizable or strongly factorizable varieties. And there is a technique given by Sakaridis Venkatesh to try to reduce the conjecture to these cases. So, okay, and now I come something which is not, which does not exist for periodic groups. This is the algebra of G invariant algebraic differential operator on X. So I recall X is a complex point. One introduce a switchable maximal split Cartan subalgebra of G. G equals T plus A, and AX is the quotient by the intersection with HC. Let S be the simple spherical roots of X, and there is a Harish-Chandra homomorphism of Knop, which is an isomorphism between D of Xi and 0x plus A star X WI, where rho X is the half sum of G roots of a certain Borel subalgebra of G containing of G containing J, and WI is a group of orthomorphisms of X generated by the reflection around the elements of the set I of element of S underline vanishing on AI. What? This, maybe not, but I'm not sure. But what I want...
maybe it's the center of the effects in general? Maybe this is the center of the effects in general?
I don't understand.
I thought Stokes' theorem...
No, but what I want it is to be true for spherical...
But you want real spherical. Your X is real spherical. So
No, I do it for complex.
right. So over the complex numbers, X is not spherical.
Okay. But the theorem of Knapp is nevertheless true in that case.
I think it's about the center of this ring in general. This ring is not commutative in the non-spherical case. You are right, man.
Yes, you are right.
You're right. It's the center of the ring. Right?
Yes. Maybe I made a confusion here. Okay. And Q10 related this homomorphism to one has been defined a few years ago by Bézard-Plessis, essentially, which is given in terms of the round-jumping algebra of P is much more closer to the definition of the Harish-Chandra homomorphism of the Harish-Chandra homomorphism. So, okay, I should have said this before. I assume that X is absolutely spherical. This means that the X complex is spherical. The self-adjoint part of D of Xe acts by essentially self-adjoint operator on L2 with common core, the space of C-infinity vector of this representation. This was proved by Van den Baan for symmetric spaces, and the proof here is not so much different. And what is important with this property is that it's allowed joint spectral decomposition, because operators are commutative and you can do this. And so I will come to the core of the subject. Together with the conjectures, the result of Kreutz, Kuit, Obdam, and Shishkrul on the infinitesimal character of TD and the description of D of X above, this allows us to show that L2 of X TD is the image of the spectral projection attached to some part of its spectrum. TD, and this proves that the measurability which was needed to make the invert integral of this twisted discrete series. Qu'est-ce que j'ai fait là? For this, we use a property of spectral projection of type 1 groups, which was given to me by Alan Cohn. It says that under some hypothesis, something which apparently is very trivial, the spectral projection for an Hilbert integral of representation is the Hilbert integral of the spectral projection. So this seems very natural, but this is not completely obvious. So, okay, this ensures the measurability I wanted for the twisted discrete series. And so now coming the Bernstein morphism. There are G maps from the L2 with the boundary degeneration to L2 of X. Given in the Plancherel isomorphism. So I recall you have the Plancherel decomposition for L2 of X and the Plancherel decomposition for L2 of Xi with the same measure. And so you can define this Hilbert integral. So GIP are these maps, and EIP are just the tensor product of the identity with GIP. And it works because we have the same measure here and here. And this is very important. The Bernstein morphism are abstract version of wave packets of Eisenstein integrals. Abstract because these maps are not explicit. This space is not explicit and this space is not explicit. The goal is to, at the end, should be to make this thing explicit, of course. Now I come to scattering operators. So this was done by Sakaris Venkatesh for periodic spherical spaces. The first thing is that so II is a Bernstein maps which goes to L2 of Xi to L2 of X. And the sum of these things is L2 of X. So this is not far from the decomposition of L2 of X, but this is only a sum and not a direct sum. I define IITD, the restriction of II to L2 of XTD. Okay, this is a restriction of the Bernstein maps. So it maps L2 of XTD in L2 of X, not L2 of XTD in L2 of X. Using a spectral projection for Z of G and decomposition of L2 of X. One shows I will the G equivariant map EETD composed with this adjoint from L2 of XTD to L2 of GTD is non-zero if and only if AI and AJ are conjugated by WX, by the Val group. Which I will denote E approx G. Again, using spectral projection for A0 and A0, it is relatively easy to see that if I is approx G, there exist operators, scattering operators, SW, for W in the set WEG of elements of WX which conjugate AI to AG, such that decompose the composition of the restricted Bernstein maps and is adjoint, and moreover they are they satisfy comment je vais dire some intertwining condition. Okay. And the SW, I don't say, they are intertwining operators. They are intertwining operators. They are yes, it is written here. And the big step in the proof of the Plancherel formula that will follow is to prove that the scattering operators are unitary. In some sense, they are Hilbert integral of unitary operators. Bon, try to say something about this. I think very quickly. So I have. So the main theorem is the following. If I have three subsets of S, which are approximate, you have this relation between Ij and IITD first. They compose well with respect to the product of elements of the Val group. And I already said that they verify this property. Okay. And now is the main theorem. So C of I is constant, and there is a isomorphism between L2 of X and the direct sum of the L2 of XTD, but so this is an embedding, and it is an isometric isomorphism onto the subspace of Fi, which are preserved by the scattering operators. But once again, this is not the end of the story, because one has to understand what the spaces L2 of XTD and the Bernstein maps. And Sakaris and Venkatesh were bounding the L2 norm of the restriction of function on X to neighborhoods of infinity in a smooth compactification of X. We do something similar, but there are some argument, because the argument is rather specific. covering of X. So you have X and the compactification, and you have the closed orbit, and you take a neighborhood of this closed orbit. And after you continue to cover the rest of X. So let us assume that X has a wonderful compactification. The G orbits in X are in bijection with I in S, YI with closure ZI. And now it is there is a definition of the boundary degeneration. You have YI, which is in the compactification. We can look to its normal bundle, and Xi, the boundary degeneration is the open G orbit in the normal bundle. I think here that unicity of open P orbit is required to have this kind of thing. One ends up with a covering of X by a finite family of open sets. UI, so they depend of I on a finite set I and epsilon I. The parameter epsilon I is positive, and it measures the proximity of the boundary to the boundary orbit YI. You have a neighborhood, but you can be closer to the orbit. And what was missing in a previous version of this work, that there exists a C-infinity map, EI, which I call exponential mapping, but maybe it goes on the other direction than the exponential mapping of Seridis and Katesh. So I take a boundary of Zi in X bar and a neighborhood in the normal bundle to X bar. And so this is here. It is important that it is not it is Zi and not YI. And I want this map to induce the identity between the normal bundles, the normal bundle first, the normal bundle first, or normal bundle to Zi, and also the normal bundle to this, but the normal bundle of the normal bundle. And I want also that the intersection of G orbits with the corresponding G orbit are corresponding by this exponential mapping. Okay. Okay. In particular, UI, I recall UI is the neighborhood of YI. Is a subset of a translate of the open P orbit in X. the open P orbits in xi correspond and are in bijection, and the UI are, by the definition I gave, they are translate of the subset of a translate of this open P orbit, and it corresponds to the corresponding translate of the open P orbit. So, function on the restriction of function of f to ui might be viewed as function on ui. Qu'est-ce que je veux dire par là? And the constant term of the restriction fi of f to ui might be viewed as function on ui. So you can form the alternate sum of these objects, of this constant term. And what I call, I got a sharp inequality for this alternated sum, and I call this the main inequality. So this is one ingredient, one important ingredient, and then the elementary analysis, like the Plancherel formula for Rn, is used to bound the L2 norms of Fi for most I, and some I requires the use of exponential mapping. And this leads to the unitarity of scattering operators, and the main theorem follows the CD. You have a question?
That's for most I.
All I are not equivalent. I will not be able to say which I are not good, but some are not good. I think that let me try to remember. No, I cannot say. I will tell you later, but there are two cases. One doesn't need the exponential mapping, and one requires it. David, you don't make a nasty remark.
How do you explain this? But since you say that the main thing you have to do is prove the unitarity of the scattering operator, and you describe how to prove a series of inequalities, it's hard to understand how you can use inequalities to deduce that something is...
No, but yes, the point is you suppose that it is not unitary, that there is some inequality in the wrong sense up to, I think it is the blackboard, the S of W is greater to the norm of V minus epsilon, and then you start with inequalities. I think you want to prove that S of WV is greater than the norm of V. Because if you have this, because you have the inverse of the scattering operator, you are done. So only one inequality is needed. But you are so good. Thank you. It was not so bad as usual. That's it.
Any more questions?
When you put unitarity, you're assuming it's not unitary, and therefore there's some inequality, or?
No, I think I proved that, and as you did, that SWV, the norm of SWV is greater than the norm of V. So you start to prove this. If you prove this, because SW minus 1 has the same property, you will get the right inequality.
So can I ask you, the Puncherel formula, the Puncherel formula that you arrive at is the sum over subsets of spherical simple roots. Is there a corresponding statement about parabolic subgroups of some kind that, you talked about these degenerations of H, but it sounds more complicated than the classical parabolic subgroup stuff. Well, I understand the combinatorics of subsets of what kind of set, but...
No, but for example, what is not known is if these pieces are induced from parabolic.
And you said that's not known.
That's not known.
I think it's known that they are known. So I think what is nice about Martin Ford is that he doesn't do an assumption, a technical assumption that he can eradicate, which forced those states to do that and look at the use. Without that assumption, the examples for these states are not parabolically used.
This is really hard to believe because it sounds like you have, in the real case, a family of representations whose infinitesimal characters lie in a certain affine space, and such a family has to be parabolically induced.
No, the problem is the conjecture, okay? Of course, the conjecture doesn't say that twisted discrete series are coming into families, but it is obviously what we think that they actually you conjecture something like this, but you see, twisted discrete series is much more complicated than relative discrete series, because for relative discrete series, you take a discrete series and you twist by you tensor by a character. But for twisted discrete series, this is not something like this. You can have a given discrete series, and then you don't know what to do to get a family of twisted discrete series. This is voilà. This is
So is what I said incorrect, that this family, the infinitesimal characters are not known to lie in some affine space?
That's more or less the conjecture.
yes.
That's more or less the conjecture that the character basically is the imaginary part, and orthogonal to that everything is real and lies in the lens.
Bon, c'est pour dire que c'était très mauvais, c'est ça?
You said we a couple of times. Is it the nous de majesté or is this commonwealth?
I thought.
Is this commonwealth?
No.
No, that's your.
No. Yes, it was a we of majesty.
Okay. And the other question is, actually, is it easy to go back to the statement of the main theorem?
Yes.
Okay, yes. Because my question is, so finally, how explicit is this Blancherel decomposition?
Yes.
Do we know the masses, the measure, exactly?
I don't know, but for symmetric spaces, the question of the Blancherel measure for group, there is the notion of Blancherel measure, which is well defined. But for symmetric spaces, and I guess for spherical spaces, there is only a class of measure.
Oh, I see. Okay.
First. Okay. Then after, what is and you see these things, they live as a direct integral over lambda. Maybe so the measure is absolutely continuous with the big measure, but it's not clear if there will be things all over the line or the vector space. And second, the twisted discrete series is a big problem. Okay, I have not finished my talk actually. So problem. For my conjecture, I don't need completely the complete knowledge of discrete series, but I think this is a challenging problem for people working on unitary representations to deal with with this problem, because the only work is a work by Oshima Matsuki, which is already hard to follow, and it doesn't work at all in this case. Yes.
Well, one can say in addition that your conjecture would follow if we could show that the infinitesimal character is regular. And this is not what we were able to show. And actually that's a
show that the characters of this lead series of regulate something which will generalize. This will give in particular this lead series of so regular means for the spectrum of the algebra of differential operator with respect to this Cartman subspace.
You are going to make some comments about the multiplicity space. You said you will make some comments about the multiplicity space.
Yes.
I mean, what does it look like?
No, yeah, this is totally unknown. Okay. For example, a representation can appear with multiplicity greater than 1 as a discrete series. I think it is not known if it is possible or not to have a discrete series with multiplicities greater than 1. So, okay, so this is already a problem. If you don't know this, it is difficult to say something about multiplicities.
So the space you wrote down of H invariant tempered distributions, that's known to be finite dimension.
Yes, yes.
And how large a subspace, and you know examples where the unitary multiplicity space
It's smaller.
that's related, how different they are?
No, I don't know.
Well, you know, it's the verb of drop and eta, I think, for the most completely spectrum. Then multiplicity spaces are
Yes. Okay.
so there's one case, the most completely
Yes. What has been done by Kuit and Sayag, they determine the case where I is equal to empty set. And they determine L2 of X. So the contribution to the Plancherel formula of the empty set. And here the representation are induced by some parabolic. Yes, it's a very nice work.
Any more questions? So let's thank the speaker again. And we take a 5-minute break and meet at 5 o'clock.
Écoute, en tout cas, j'ai tenu les oreilles.
Je te parle pas parce qu'on est
Oui, oui, attends,
en direct là.
ouais.